Okay, welcome back. Physics is kind of where we're headed here. 7.5, we're talking about work. Um, so work done by a constant force. We just want to know the formula for that, and the formula is just going to be force times the distance traveled. You don't have to worry about projections or anything. So probably in physics, you worried about problems where a kid is pulling a wagon with force going in this direction and figure out the work going from here to here or something. We don't even go that far. We're just in the beginning, because some people have maybe not taken physics yet. This is all we care about. It's just a force in the direction of travel. Figuring out the work is just a matter of multiplying the force times the distance. Okay, so problem 3, they start you out easy. You're given a force of 112 newtons, and then you want to find the work done by pushing the block 6 meters, or rather 8 meters. So you'll note that's easy. The work is just 112 times 8, which is 896. And for the units, you can just borrow whatever units you're working with. Make sure within the problem everything's consistent. But if you're given newtons and meters, just leave your answer in Newton meters. Okay. All right. So taking it up a notch, we then talk about variable force. But again, we're always kind of doing force in the direction of movement. So anyways, we could use an integral to model these scenarios, work by variable force. So the force is variable. That means it's dependent on the, well, in this case, I guess, position. So you'll be given some force function, maybe something like this. Okay. And then to figure out the work done by this variable force, going from, I guess, position A to position B, all you need to do is chop it up into a bunch of little blocks. And the area of these little blocks will tell you the work done in each little subinterval. And then you just do your running man again and allow him to accumulate all these work increments. So now instead of stealing up a bunch of volumes, your little criminal is going to go through and steal a bunch of what they'll call work increments, okay, these delta W's. Okay, so let's just notate this. F of x sub I, what is that? Well, that will be the force required at that particular location. And then this increment thing that the little criminal is running through and picking up, this work increment, that's just going to be the work done in the ith interval. And the formula for that is exactly the formula for the area of that little rectangle. But we know it's force times distance, so force given by the force function, f of x sub I, times the distance traveled. And of course, this distance traveled is just our delta x, the base. So it turns out to be the same formula that you used previously. But now we're modeling work in physics. Okay. So at the end of the day, the work will be the limit of the sum of all these work increments, which will give us the integral from a to b of the force function times the distance. So it's basically just this FD, FD. Alrighty then. The book will kind of give you a bunch of examples in the intro section, and within the examples that give you formulas, you need to create your force functions. So there's a propulsion problem, there's spring problems, so what do they call it? Hooke's law, and then we have some sort of variable type problems where we're pumping stuff out of cones, and they're kind of weird. So anyways, the formulas for force, we don't expect you to know those like off the top of your head or something. What I'm saying is you could look in the book and figure them out because they'll be given in the examples. So first, propulsion. The force formula they're working with is the force is inversely proportional to the square of the distance of the object from its whatever's pulling on it. I guess this seems like a distance formula between two objects. Okay. So anyways, what's going on in this problem? We want to know the work done in propelling a 10-ton satellite 11,000 miles above the Earth. Right. Okay, so I need my force function, and right now it has this unknown constant in it. So let's take a look at the picture. Here's the Earth. Here's my little satellite. It weighs 10 tons on the Earth at this point. So you think of 10 tons as a force, right? It's the force exerted by, I guess, the gravitational pull of the Earth, right? So here we're presuming that the radius of the Earth is 4,000 miles. In other words, we could use this information in order to solve out for the constant c. Okay, so we have a 10-ton satellite. 10 equals c all over 4,000 squared. Okay, so our constant c will be 10 times 4,000 squared. Then we can plot that in for our force formula. So big F of x must equal 10 times 4,000 squared all over x squared. Then to find the work, it's just the integral of f of x times dx. So it's 10 times 4,000 squared all over x squared times dx. Maybe the only problem is just figuring out the bounds of the integral. And you got to be a little careful. We're actually starting at 4,000, and then we're traveling to 11,000 miles above the Earth, which will be 15,000 miles. Okay? Right, so we want to travel an additional 11,000 to here. So in other words, on our integral, we're going from 4,000 to 15,000. Okay. And then if you evaluate this integral, you should get 29333. Our units miles and tons, so mile tons. Okay. Right. Let's look at Hooke's law problems. So 7, we have Hooke's law that you'll play around with a lot more once you get the differential equations. Anyways, this is force equals, the force is proportional to the distance from the equilibrium position. So, depending on the orientation, you have some spring attached to a wall of some sort, and then maybe a weight attached to the spring. And then the farther you move it away, the larger the restoring force is. Okay? So that's kind of what we're talking about. So maybe this is our equilibrium position. Okay, okay, so in the problem, we have a force of 20 pounds stretching a spring 9 inches. And I think their orientation is probably, I don't know, I'm guessing it's like this. So the weight is stretching the spring 20 inches. Force of 20 pounds stretches the spring 9 inches. Sorry. Find the work needed to stretch the spring 1 foot. Okay, so we use the first bit of information to solve out for our constant. So the force is 20 when the distance is 9 inches. So our constant is going to be 20 over 9, and then that gives us our force formula. Okay, so our force formula is 20/9 times d, or if you'd rather, you can use x. Okay. Right, so we want to know the work in stretching this string out 1 foot. Okay, so we're going from some equilibrium position to 1 foot, so 12 inches. So you have to make sure you're consistent with your units. If the force function is in terms of feet, you want your integral to be in terms of feet as well. So anyways, we got 20/9 x dx. And then you just integrate that thing. You should get 160, and our units are inches and pounds, so inch pounds. Okay, so these types of problems, look for the formulas. They give you information that will allow you to solve out for the unknown constants, and then you just plop those force functions into your integrals and integrate. Make sure your units are correct. Make sure in these weird kind of problems your bounds or your limits are correct. With the spring problems, sometimes they'll say find the work to stretch the spring an additional 1 foot, so you'll be starting at 9 and then going to like 21. They try to trick you, but at the end of the day, these problems are fairly simple. If you're getting them wrong, it's because of something silly. Okay, so let's move on to maybe the harder ones where we have to think a little bit more. Okay, so section 3, fluids and chains. Number 19, I'm pumping a bunch of liquid out of a cone of some sort. So I'll orient the cone on the XY axis. 1, 2, 3, 4. So this point is at 4, 6. 1, 2, 3, 4, 5, 6. So I have this cone. It's full of a liquid, and I need to calculate the work done in emptying the tank. Okay, so the deal is going to be like this. I'm going to section it up into a bunch of little discs. Okay. And then figure out the force required, figure out the work required to push each little disc out of the cone. Okay, so I need to figure out the work required to move this particular disc of water out of this cone. This is just a cross section of the actual cone that I'm pumping the water out of. So I'll find the work needed to pump this disc out of the cone, and then some. We want to do that for each one of the discs. So our little criminal guy is going in this direction, and his bag is full of these work increments. Okay. So I need to figure out work increments for each one of these discs. And So first I need a force increment, so to speak. The force to move out a particular disk is going to be just the weight of that particular disk. Okay, and the weight of this particular disk, what they're going to have is kind of a density constant. So density per unit volume, or mass per unit volume. Sorry, yeah, it's pounds per cubic foot in this case is what it's going to be given as. So we have 62.4 is the weight density. Yeah, that's the word I'm looking for. Sorry, weight density of water. And the units on this thing are pounds per cubic foot. So in order to get the force, you need to multiply this by the volume of this. So the volume of this would be in cubic units. It would cancel with this cubic measurement and leave you with pounds, which would be the unit for your force. Okay. So I need to know the volume of this particular disk and figure out the volume of that. That's just going back to kind of like last section. So this disk located at this particular Y location will have volume pi r squared h again. So this guy has volume pi, then r squared is the radius of this from here to here. So I need a formula for that, which will be this line, the formula for this line, but in terms of y. So I need that thing, and then times the height, which is just change in y. So to get the formula for this line, you can use the point slope formula. So it's going through 0, 0 here, and then 4, 6 here. The slope in that case will be 6 all over 4, so it would be 3 halves. And so my equation, y minus 0 equals 3 halves times x minus 0, but I need it in terms of y. So then I got to translate it into x equals 2/3 y. Okay? And then that formula will give me the distance from here to here. And so I know the distance from here to here is really just the radius of that particular disk. So I have 2/3 y squared, and then that will be the volume I need to multiply by this thing in order to get the force required to move this particular disk. Okay, so it'd be 62.4 times pi times 2/3 y sub I squared times change in y. Okay. Okay, so all of that is just to get my work increment. And of course, the work increment is just the force increment times, so this times the distance traveled, right? So I still need one more thing. I need to know the distance from here, this y sub I, to the top of the cone, because that would be the distance that I'm having to travel. So I need to push this object from here to here in order to push it out of the cone. So what is that distance from here to here? Well, that distance is just this distance to the top of the cone minus this distance to that particular y sub I location. Okay, so what is that? Well, that's 6 minus y. So it would be the force increment times 6 minus y sub I. Okay, and then you just add all that junk up. So at the end of the day, it's going to be 62.4. I'm factoring out all my constant material. Pi times 4/9 integral from 0 to 6 of what's left over. So we got the y squared, I guess is it, and then dy. Oh, and then I lost my 6 minus y. Sorry. So it's this thing that the running man is adding up and throwing in his bag. It's the work increment. So I need to also multiply in then the distance traveled, 6 minus y dy. Right, so all of this material up to here represents your force increment. And then when you multiply all that together, you get your work increment. So the force increment should technically also contain the d sub y, the dy, sorry. Okay, so there's our integral, and then you just turn the screws on it and get it done. So recapping, I guess, I needed to find the work in order to push all of the liquid out of this cone. This cone, as it sits in this picture, is just a cross section of the cone. So what I'm doing in order to figure out the work is to chop up the water inside of the cone into a bunch of these disks. Okay, so to figure out the work required to push each disk then out of the cone, I needed to figure out the force required to push the disk out of the cone and then multiply it by its distance. To figure out the force, I needed to take the weight density of the water, which is just a constant that's given in the book. Okay, they're well-known constants. You could Google them. Okay, so that's the weight density of water, and it's in pounds per cubic foot. So to figure out the force, which is just going to be the weight of the water in this particular disk, I take the weight density and multiply it by the volume of that particular disk. To get the volume of this particular disk, I needed to figure out the dimensions, the radius, and the height, because the volume of this disk is the volume of this basically smushed cylinder. It's pi r squared h. So it would be pi times the radius squared. In order to figure out this radius, the distance from here to the outer part, that's the distance from here to here, I needed to figure out the equation of this line. In order to figure out the equation of that line, I had to figure out basically the slope of that line. So I have this point given as 4, 6. This point is given as 0, 0. So the slope is 6 minus 0 over 4 minus 0, which is 3/2. And so using point slope form, it's y minus 0 equals 3/2 times x minus 0, which is y equals 3/2 x. For this orientation, I had to put it in terms of y, so I solved for x, and I got x is 2/3 y. That gives me, for any particular y sub I, the distance from here to here, okay, which is, again, the radius of this particular disk. So the volume of that disk is pi r squared h, pi times 2/3 y squared times change in y. So here we have weight density times volume, which will end up in, the units will be pounds. And then to get the work required in order to move this particular disk out of the cone, I need to multiply the force required to move the disk times the distance the disk actually moves. So the distance the disk actually moves is going to be this distance, which is 6, minus this distance here, which is given by y sub I. That will tell me this particular distance here, which is the distance this disk needs to move. So it'll be change in force times distance, the force increment times the distance for that particular cylinder. And then my little criminal needs to go through and accumulate all of those work increments. I do that with the integral. So ultimately I'll have the integral of this thing right here, which will turn out to be this guy right here, okay, without the messy business there. Integrate that, and that tells you the work. And it should be in pounds, foot-pounds. Okay. Oh my gosh, okay. The last problem then is the chain problem. So this is 27. And the scenario is some sort of crane mechanism, and it has a winch at the top of it, and it has a chain kind of hanging from the winch. Okay. Okay, in this particular problem, the length of the chain is 20 feet, I believe. And the deal is the operator is moving the chain to the 10 feet level. So this person wants to roll the chain up onto the winch until there's only 10 feet of chain left hanging. Okay, maybe they need to attach something to the chain. They need to figure out how much work is done in doing that. Okay. So before we had this idea of weight density of water. Here we kind of have a chain density. So the density of the chain is going to be 3 pounds per foot. And I'll say that's the chain density, I guess. Okay. So in order to figure this problem out, we're going to, again, kind of split it up into a bunch of little force increments first off. So we have these change in F sub i's. You can orient this situation in the xy plane, I guess, like this. So I'll put 0 at the bottom and then 20 up here. And then I have my chain on this y-axis. So the force required for any particular bit of chain, let's say at location y sub I, where the width here of the length of chain that I'm worried about is change in y, the force required to move that little bit of chain is going to just be the chain density, which is 3 times the length of chain, which will be change in y. Okay, there's actually 2 kind of distances traveled, right? For the bits of chain up here, they don't have as far to move. So we're not going to consider the work required to move the chain on the winch as it goes around. Okay, so I just want to know the work required to move this bit of chain from here to here. Okay, so this bit of chain will move farther than this bit of chain. This chain will move from here to here. This bit of chain will move from here to here. And then all the chain down here will all move the same distance, right? Because they're not going to get onto the winch. They'll always be moving by 10 feet. Okay, so there's 2 kind of work increments I need to worry about. I'll say we'll call one change in W superscript 2, and then the other one change in W sub I superscript 1, I guess. Okay, so for the bits that are close to the winch, the distance traveled is going to be 20. It's going to be these kind. So let's pretend I'm at this particular y sub I distance. The bit of chain here is going to have to travel this distance. So this distance is a difference. It's the difference between this distance, which is 20, and then this distance right here, which is y. Okay, so for any particular bit of chain in this interval from 10 to 20, the distance traveled will be 20 minus the position of the chain. And then, of course, we have to multiply that by the force increment, because work is always force times distance. For the other guys, then, it will just be F sub I times the distance traveled will always be 10, right? Okay, so we need 2 integrals in this situation. I need an integral from 10 to 20, and in that case, it's going to be summing up this junk. Okay, so the force increment, we have 3 times dy, but we want to put the dy at the end. So it's 3 times 20 minus y times dy, and then plus the integral from 0 to 10 of 3 times 10 dy. And then if you add up all that business, you get your work, your total work. Okay, let's leave it there. Thanks for watching.